Okay, so now we have our boundary that we've created or delineated with our information. And now we're going to go in the last part, which is section 4. And again, as I mentioned, all these sections connect. In section 2, remember we did the building footprints, and that's helpful because it helps you make population estimates that then is useful for humanitarian aid. In section 1, we used a settlement boundary. In section 3, we're making our own with the k-means classification. But in section 1, we did a lot of land cover change analysis, and we looked at land cover conditions, land cover changes at Pajarinia, and we used that information to help map the extent of the settlement. So now in this case, we're going to be using satellite-derived data to estimate the size of the refugee population living there. So as I mentioned, it's really important to know how many refugees are at a settlement to estimate the need for food aid and just for guiding sustainable development and disaster risk reduction efforts. So satellite-informed population estimates can be useful for that, especially if there's no other data available. So in section 2, we talked about those building footprints, as I mentioned. Section 4, we're diving deeper. We're going to work with a lot of different data sets used to estimate the geographic distribution of human populations. So you've got these three, and then we're going to compare with the UNHCR recorded refugee population data from September 2020. So these are the four that we're going to be working with. And we're basically, each is based in part on remote sensing detection of buildings. And we're going to analyze population estimates at the Pejarinia refugee settlement from the global human settlement layer, the GHSL. So if we go copy paste from our checkpoint D, we can look at the three data sets that we'll be using today. And we can also extract the one that we'll be comparing it with to see if our work is doing anything good. Okay. Okay. So before we run it, I'm just going to show you. So these are the variables that you're creating. Again, you have your basic map center object, and then you're importing these three population data sets. So with this one, this is the Pajarinia refugee settlement from the global human settlement layer. So global human settlement layer. It's good to look at the bands because we're most likely going to be using the population count. And then we're going to be using the high resolution settlement layer. Again, the importance of high resolution I mentioned earlier, because when you're dealing with sensitive data like this, that can get mixed up with the other spectral indices and the features that are in the same region. If you have access to high resolution, among the challenges that you face, it's one of the better solutions. So this one might not be necessarily reachable because you can import data sets. This is Project Gbook. So I'm going to guess that this is an image that we cannot get from the catalog. And then we're going to use some World Pop data products, which you have used. If you've looked at other applications, you should have looked at World Pop. It's a pretty common one. And so this is for, I believe it was A1.4 that might use this population if you've done it. So in this case, the 100-meter one is for one we're going to be using. And you can just confirm that from here. But again, this might tell me that it needs fixing. Sometimes the names will change. So just use what's there. But this is usually the data catalog is pretty useful for searching your data sets. Okay, so we're going to go through this, run it, and see what it gives us. So let's start. So we're working with HRSL and World Pop here, which are data sets from 2020, and then you've got GHSL available for multiple years, but we're using most recently 2015 to 2016, so about pre-establishment. We're filtering the GHSL image collection to only the data sets, population count, and we are renaming all the bands to population for consistency because then when we do the visualization, everything's consistent and runs smoothly. Then we're also mapping all population maps using the same visualization approach to better support a direct direct comparison. And we're gonna map all the population data sets just so we can visualize them first. And I already ran this because it takes a bit of time. So let's look at them. So we've got the GHSL here, in centered around Pygorrhenia. We've got, sorry, this is GHSL. We've got HRSL population. And so it's gonna be hard to see, but you can see it here. And then you've got world pop. So HRSL pretty much on the boundary here. And HRSL is from the assets. So there could have been something done already to it, but I don't have any information on that one. You've got world pop and GHSL. So already you can kind of see that it's showing up around the boundary, which is good. And then the other thing you can do is use the inspector tool and click the values. Okay, a lot is going to show up here, but you're interested in the population ones. And with the inspector tool, you can identify the different pixel level values for each population data set within and around Pygorrhenia. And the values you see represent the human population estimated to be present at each pixel in 2015. So in our case, it's going to be pre-establishment because 2016 and over is going to be post. Okay, so you can use the inspector tool for more information, but basically should give you values representing the human population estimated. So once you've set up your visualization parameters, you've printed your map, you have an idea of what it looks like. Each dataset has a different spatial resolution, and it's important to note because we're going to need to know the different spatial resolutions when we summarize each dataset's population estimate across the Pygorrhenia boundary. And that summary will be done by the function you've seen many times by now, which is reduce regions. So first, you're collecting spatial resolution for each dataset. Then you're summarizing the population totals, so with sum. And then once that's done for each data set, you've got your Pygorrhenia with population estimates. You can then assign as new properties to the UNHCR boundary feature. So you measure difference between settlement product and UNHCR recorded population values. So once you have the population estimates, we can add it to the Pygorrhenia feature as a new property. So Pygorrhenia get UNHCR pop, Pygorrhenia get GHSL, Pygorrhenia get HRSL, and the Pygorrhenia is what you had done here, and this is where you had set your reduced region because you're summarizing population totals for each population product at each settlement. And as you do that, you're assigning as new properties to the UNHCR boundary feature, which is Pygorrhenia. So you're doing all of this in these in this function. And when you've done that, you have the Pygorrhenia with population estimates. We'll print that. And then you'll have three very different population estimates for Pygorrhenia based on three population data sets. And then we're going to be able to subtract it with the UNHCR population because this is population that was recorded in 2020 post-establishment that is also stored as a property of the Pygorrhenia feature. So here, what we're doing is subtracting the UNHCR population total from each data set's estimated population total that we had done here with sum. Then we're storing each difference as a new property. So GHSL diff, HRSL diff, and so on. And once that happens, we're doing the same thing that we had done here, where we were assigning as new properties to the UNHCR boundary feature Pygorrhenia. Now we're updating the UNHCR boundary feature with population difference properties. So you've got Pygorrhenia set, and then you got your dictionary from lists, GHSL difference, just here, HRSL difference from here, and world pop different. So you're just adding it to Pygorrhenia. So when you print Pygorrhenia population estimations, this time you're getting the difference. And whether or not it's a positive or negative difference is going to indicate the estimation of the UNHCR population. So If we get a negative difference, it's going to indicate an underestimation of the UNHCR population. And if you have a positive difference, it's going to indicate an overestimation based on your reduced regions. So in summary, you collected the spatial resolution of each data set. You've summarized population totals from each data set. You've assigned as new properties to the UNHCR boundary feature. Once we have these population estimates, we've added it to Pagarinia as a new property. Once you have these three very different population estimates for Pagarinia based on the population data sets, you consider the population recorded in 2020 by UNHCR post-establishment. That is also stored as a property of the Pagarinia feature. And to do that, we subtracted the UNHCR population total from our estimates. And now we've got population differences here. And we've got population difference properties that we've added to Pagarinia. And now we've got Pagarinia population estimations. So remember we had collected, so while it's running, remember we had collected spatial resolution. And the reason I mentioned that it's important is because when you're doing this reduced region, which is what we are doing to make these population estimates, you need a scale that's going to be accurate for what you're doing. And so when you're setting the scale here with projection nominal scale, and the function here, then you're making sure that each scale is relevant to the data set. So this is where your scale shows up and why we've done this here. You do projection because from this you can determine the native resolution of the image, and then you have nominal scale because the native resolution is the nominal pixel scale in meters, and then you've got your world pop scale. So now we have our results. What's happening in the console? Okay, so GHSL, you've got 100 scale, 30 meter scale, 92 meter scale. And then you've got your Pagarinia with population estimates. GHSL, you have your population estimates here. HRSL, UNHCR POP, World POP, you've got your estimates. What's the year estimate? 2016. Again, this was our first one. Then we had our population estimations here, but these are the difference properties. So for GHSL difference, you've attached a dictionary from list. So this is what we mean by when we're attaching, we're doing Pagarinia get, we're adding it as a feature property to the boundary. So we're just assigning new properties to this feature, and that's why we have it all together here. So as you can see, if you're subtracting GHSL from UNHCR POP, there's clearly an underestimation, and you can see from how much. If you're doing HRSL and UNHCR POP, on this case, again, there's an underestimation. In pretty much every case, it's been underestimated because it's minus. If this had been positive, then probably World POP would have been way bigger than the UNHCR POP, and then you would have determined an overestimation. But the one thing that I am unclear, and there's not much about it in the book, that may be unclear as well for you, is that, we have two data sets here that are working with 2020, and then we've got the HRSL that is working for between 2015 and 2016. So this, we don't have much information, but if we look at this one here, so dataset availability from 2000 to 221. But in this code, we're not looking at we're not filtering for a specific date. So as we come to the end of section 4 and the end of this chapter, I invite you again to go look at the questions offered in the book and see if you can challenge yourself and work on your understanding of the code. For example, when we had worked with the k-means boundary, and now we have the population data sets, which I'll minimize a bit here. Think about the coverage of the world population data at Pagarinia. It's not fully contained in the UNHCR settlement boundary. So determine whether or not this spillover is better captured by the k-means boundary from section 3, for example. Because earlier in section 3, we were comparing the different boundaries, determining whether or not one boundary was encapsulating more information than the other, or if, the k-means boundary was good at separating the settlement from other things um, that are found outside. So let's see, for example, if we look at world population data, and then we look at our two boundaries. I'm just going to take away this information. And this is just things that you can do on your own time, but I'm just going to look at it. You've got the Pagarinia refugee settlement boundary. You can see that there is some spillover right around here. So if you take this out and then you put the K-mean settlement boundary, is that being considered more than the UNHCR settlement boundary? Is the spillover being better captured by our K-means boundary from Section 3? So it's just we do all of these different things comparing with something that exists and something that we're making to compare and always analyze the efficiency of data and what your classification is doing, what your estimation is doing, and revisiting when it comes to dealing with human applications. Because, as I mentioned, the importance of these humanitarian applications in Earth Engine is because this then helps further actions like humanitarian aid and knowing what's in the area and what's happening to the land in that area and so on. And you're building from existing data sets, but you're also making your own. And it's important to understand how these data sets interact with each other and how they may be useful. In the end, I hope that this has given you insights on what kind of humanitarian applications can be done in Earth Engine. And if you're thinking of refugee settlements, what are some challenges that you might run into? And what are some things that you can do in Earth Engine with regards to that? So we're going to end with our conclusion. And basically, this chapter introduced you to many different approaches to characterize land cover dynamics in and surrounding the Pajarinia refugee settlement using a range of open access satellite data and geospatial products. We saw that satellite remote sensing approaches are effective for characterizing land cover changes before and following the establishment in 2016. And they're also useful for delineating a refugee settlement boundary that represents land directly affected by the settlement's establishment and use. And this was through the use of building footprints, our K-means classification, our land cover classifications, gouging changes in land cover, and our spectral indices. And then we noted that there was also significant discrepancies and inaccuracies in population estimates from satellite-informed data sets, which goes to show that there remains challenges in these operations, and it's important to compare. It's important to test different things. And it just highlights the value of remote sensing for long-term refugee settlement monitoring, because the more you practice, the more you use the data, the more you try different things, the more comprehensive it becomes. And it just emphasizes the need for better integration of humanitarian data in remote sensing applications. And this can be done by including more scenarios, more locations, more refugee settlements. It's only a problem that is increasing due to many different causes, such as natural disasters, war. And so I think that it's hopefully today this chapter has taught you a bit about the surface of what can be done for humanitarian applications, as I mentioned earlier, and that you've left with some key learnings from this chapter, as mentioned in this slide. So I invite you to look at the other chapters if you're interested in other applications. Thank you.